Hi guys, this is Acid Base 101. This is part 2. And what I'm talking about today is the autoionization of water. And here are the assignments to go with the part 2. Excuse me. For the optional assignment, I want you to add on question 28 out of chapter 16. And the required AP assignment is Acid Base 2/3. And that'll be a worksheet. I'll post that on Canvas. Okay. So just as a quick reminder, we want to remember that an acid is a proton donor, a hydrogen donor, and a base is a proton acceptor or a hydrogen acceptor. And the first statement in these notes lets us know that water reacts with itself in an acid-base equilibrium. So that's our first piece of understanding here. And the reaction for this looks like this. So you have H2O, and that's a liquid, and H2O, and that's a liquid, and it reacts in an equilibrium to give us, what happens is one of these waters, it doesn't matter which one you choose, we choose this one. This water gives up one of its hydrogens, and that hydrogen goes to this water. So what we end up with is what's left over from here. We have hydroxide, and that would be aqueous. And then also we have hydronium left over, or made, I should say, once the hydrogen has transferred from this water to this water. We get hydroxide and hydronium. It's okay. So a couple things we want to notice here is that our products are aqueous and our two reactants are liquid. So if we were going to do a KQ expression for this, we would have the concentration of the products over the reactants. And so we would have concentration of hydroxide times the concentration of the H3O plus, and that would be over the concentration of each of these, which we count as 1. So we say that KEQ here is equal to the concentration of the hydroxide times the concentration of the H3O plus. Okay. And this value, or this expression, has a set value, and it's called KW, and that is equal to 1.0 times 10 to the minus 14. Okay, so we have KW is equal to 1 times 10 to the minus 14th, and that's always equal to the hydroxide times the hydronium concentration. And so this is 1.0 times 10 to the minus 14, and these have been produced from this reaction. The hydronium and the hydroxide ion concentrations are going to be the same. Okay, so a couple things that we want to remember, that this relationship is true in any aqueous environment. So the concentration of the hydroxide and times the concentration of the hydronium are always going to be equal to 1 times 10 to the 14th. So if the concentration of the hydroxide is increased, then to keep this number constant, then the hydronium concentration will go down. And that's just that's an application of Le Chatelier's principle. This is crooked. Okay, and then likewise, if the concentration of the H3O plus is increased, then the concentration of the hydroxide will go down. And so if these are equal, thank you.
Good job.
Thank you. We can have Kw is equal to the hydroxide concentration times the hydronium concentration. And if these are equal to each other, we can say that 1 times 10 to the minus 14 is equal to x times x, if we don't know what these are. And so x is equal to 1 times 10 to the minus 7. So in any neutral environment, the concentration of the hydroxide and the concentration of the H3O plus are equal to 1 times 10 to the minus 7 molar. And we'll get back to more on that here in a few minutes in part 3. Okay, thank you. Hope you're doing good. Bye.